Let's consider a few exercises from the book. This is taken from page 725. We are asked to determine whether the following series converge or not. So the series n to the minus 0.3, or if you prefer, 1 over n to the 0.3. Rewriting it this way, of course you have observed that this is a p-series. This is a p-series with p equal to 0.3, which is less than or equal to 1. And we saw moments ago that if p is less than or equal to 1, the series diverges. So it is a series diverges. It is a divergent p-series. Consider number 6. One over 3n minus 1 to the power of 4. Here, try as you may, you're not going to be able to rewrite this as a p-series. This is not a p-series. It's something to the power of 4. This is not n. So it's not, you cannot rewrite this as 1 over n to the 4. Instead, we're going to apply the integral test. The function associated to this is 1 over 3x minus 1 to the power of 4. And for x bigger than or equal to 1, there's no issue with the denominator being 0, right? So this is continuous. And positive on the interval 1 to infinity. In order to apply the integral test, it also has to be decreasing. So we're going to look at the derivative, which is easily seen to be negative 12 over 3x minus 1 to the power of 5. Is that correct? I'll let you work that out. Numerator is negative, denominator is positive, so the whole thing is less than 0 on this interval. So we're in a position to apply the integral test. Let's do so. The integral this, by definition, is the limit as n goes to infinity of the integral 1 to n. Integrate. You know how to integrate. A simple u substitution does the trick. What do we get? Minus 1 over 9 3x minus 1 cubed. Is that correct? Which is 248, 72. And as n goes to infinity, you know that this term goes to 0. So we are left with a 1 over 72. The integral converges, so the series converges. Consider this. Which is really the series n squared over e to the n cubed. I mean, you don't have to rewrite it. I'm not even sure why I just did that. I mean, it's fine. Nothing wrong with that. Again, though, not a p-series. So we have to do something else. The function associated to that is x squared e to the negative x cubed. Right? When you plug in n for x, you get exactly what we're looking at here. The exponential is always positive. X squared is always positive, so this is easily seen to be positive and continuous on the interval 1 to infinity. What about decreasing? If you take the derivative, what is the derivative? This is a product, so product rule applies. 2x e to the minus x cubed minus 3x to the 4 e to the minus x cubed. And if you factor out an x e to the negative x cubed, what are we left with? This is a 2 minus 3 x cubed. It's easy to see that if x is bigger than or equal to 1, this is going to be bigger than or equal to 1. So this whole thing is going to be bigger than or equal to 3, and 2 minus 3, or 2 minus something bigger than 3 is going to be negative. So this is going to be negative. The exponential is always positive. X is positive on this interval, so the whole thing is less than 0. In other words, we're in a position to use the integral test. Let's do so. Integral from 1 to infinity of x squared e to the negative x cubed, which is the limit as n goes to infinity, 1 to n. Again, integration is trivial. You know how to integrate this. A simple u substitution does the trick. U equals x cubed or u equals negative x cubed. Either way, I'll let you work that out. I'm sure you can read it off here. Negative 1/3 e to the negative x cubed. Which is 1/3, 1 over 3e, minus 1 over 3e to the n cubed. And as n goes to infinity, n cubed goes to infinity, e to the infinity is infinity. 1 over infinity is 0. In other words, this limit is 1 over 3e. The important thing is that it's finite. The integral converges, so the series converges. Consider another example. Number 18. Again, easy to see that, if you work out, it's not clear from, look. First of all, this is not a p-series. Very important to understand that. The function which gives rise to this, 1 over x squared plus 2x plus 2, not immediately clear that this is continuous. There might be an issue. Right, there might be a point where the denominator is 0 here. If you apply the quadratic formula, b squared minus 4ac, now you see immediately that there are no real roots. We're good to go. So this is, and since there are no real roots, this polynomial in the denominator is either going to be always positive or always negative. And at 0, it's 2. So it's always positive. So now we see that f is continuous and positive on the interval 1 to infinity. What about decreasing? We will again consider the derivative, which is easily seen to be negative 2x plus 2 over x squared plus 2x plus 2 all squared. Denominator being positive, the numerator, again you're restricting your attention to this interval, so numerator, this part in the brackets is always positive with the negative there. The whole thing is always less than or equal to 0. So we're in a position to use the integral test. Let's do it. How do we integrate? Perhaps you're thinking to yourself partial fractions, but we already argued that this was an irreducible polynomial of degree 2, right? It had no real roots. So it's already in partial fraction form. Something else needs to be done. And something else is completing the square. This is really x plus 1 all squared plus 1. I'll let you work that out. Well, I mean, it's obvious, right? If you square this, you get x squared plus 2x plus 1, plus the extra 1 gives you the 2. So, very nice. And now I'm sure you can read off what the antiderivative is. Simple u substitution, u equals x plus 1. gives you a 1 over u squared plus 1, which is arctan u. So this is just arctan of x plus 1, which is arctan of n plus 1 minus arctan of 2. And as n goes to infinity, n plus 1 goes to infinity, what is arctan of infinity? Or equivalently, right, we're asking the question, what is arctan of infinity? Or equivalently, for what value of theta is tangent theta equal to infinity? You know that to be pi over 2. So this limit here is pi over 2 minus arctan of 2, whatever that is. But the important thing is that you have a finite answer, so the integral converges, and consequently the series converges. In the next lecture that I'll upload, we'll see how the integral test can be used to approximate series.